On a clear night, the solar system can seem almost small. The moon hangs close enough to show a landscape of pale highlands and darker plains. A few planets appear as steady points of light. The sun has disappeared below the horizon, but it will return in the morning, exactly where experience tells us to expect it. From the ground, these objects seem to share one sky. In diagrams, they share one page. The sun is drawn in the middle, followed by a tidy row of planets, each one large enough to recognize and close enough to fit beside its neighbor. In it a useful picture, it is also profoundly misleading. If the planets were drawn at the correct sizes and their distances were kept to the same scale, most of the page would contain nothing at all. The worlds would shrink into dots. The spaces between them would stretch far beyond the edge of the image. Even the largest planet would become difficult to see. The true solar system is not a collection of large objects arranged close together. It is an immense volume, governed by one star and occupied mostly by emptiness. Tonight, we will travel slowly through that volume. We will begin with the scale of the system and the ancient cloud from which it formed. Then we will move outward from the sun, passing the rocky inner world, the realm of asteroids, the giant planets and their remarkable moons, and the cold populations beyond Neptune. Eventually, we will reach Pluto, follow the Voyager spacecraft beyond the main influence of the solar wind, and ask a question that has more than one reasonable answer. Where does the solar system actually end? Before setting out, it helps to establish a unit of distance. On Earth, a kilometer is large enough for roads, journeys, and maps. In space, kilometers quickly produce numbers that are too long to carry comfortably through a story. Astronomers therefore use the astronomical unit, usually shortened to AU. One astronomical unit is defined as exactly 149,597,087,870,700 meters. In everyday language, it is roughly the average distance between Earth and the Sun, about 150 million kilometers. Light crosses that distance in a little over 8 minutes. This means that the sun we see is always the sun as it was several minutes earlier. If some impossible curtain could be drawn around it at this moment, Earth would continue to receive its existing light until the final photons already in transit completed their journey. Mercury travels much closer to the Sun at an average distance of about 0.4 astronomical units. Neptune travels at roughly 30 astronomical units. Sunlight reaches Neptune after a journey of about 4 hours. That is only the beginning of the outer system. The Kuiper Belt extends beyond Neptune and contains a great population of icy bodies. Far beyond it, scientists infer the presence of the Oort Cloud, a vast and distant reservoir that may extend tens of thousands of astronomical units from the Sun. No spacecraft has photographed this cloud as a whole. Its existence and structure are inferred largely from the paths of long-period comets and from models of how the solar system evolved. At such distances, even light requires months to travel from the Sun. The system is therefore difficult to compress, not merely because it is large, but because it contains different kinds of distance. There is the familiar distance between Earth and Moon. There is the far greater distance between the planets. And there is the almost ungraspable reach of the Sun's strength gravitational influence, extending far beyond the planetary region. A small model can make the contrast clearer. Imagine reducing the Sun to the size of a grapefruit. Earth would become a tiny speck, a little over 10 meters away. Jupiter would be farther down the street. Neptune might be hundreds of meters from the grapefruit Sun. The nearest other star would not be in the next room, the next building, or even the next town. On the same scale, it would be thousands of kilometers away. The exact distances in any such model depend on the chosen size of the Sun, but the lesson does not change. Planets are not crowded stepping stones. Space is the principal feature of space. And yet, the emptiness is not truly empty. It contains light, magnetic fields, energetic particles, sparse atoms, microscopic dust, and objects too small or distant to see with the unaided eye. It is crossed by the solar wind, a continuous outflow from the sun. It is shaped by gravity, not as a visible core connecting one world to another, but as the geometry through which every planet, moon, comet, and spacecraft moves. The planets do not occupy fixed positions. They continually travel around the sun, each at its own pace. Mercury completes an orbit in only 88 Earth days. Neptune requires nearly 165 Earth years. A diagram is therefore a frozen arrangement that will immediately begin to change. The sun itself is not stationary. Along with its planets and small companions, it moves around the center of the Milky Way. One galactic orbit takes roughly 230 million years. The last time the solar system occupied something like its present place in the long circuit, the earliest dinosaurs were appearing on Earth. This does not mean the planets trail behind the sun in a simple spiral, as some misleading animations suggest. They orbit a moving star, and the whole system moves within the gravitational structure of the galaxy. There is no single stationary platform outside it from which the movement can be judged as absolute. Motion is always described relative to something else. The calm order of the present solar system can also hide its violent beginning. About 4.6 billion years ago, the system did not contain a sun or an earth. There was a cold molecular cloud containing gas and fine dust. Some region of that cloud collapsed under gravity. The precise trigger is not certain. A disturbance such as a nearby stellar event may have contributed, but the broad process is not the kind that identify in one dramatic beginning. As material fell inward, the cloud spun more quickly. This is the same broad principle that makes a skater rotate faster when drawing in their arms. The collapsing material flattened into a rotating disk, now called a solar nebula or protoplanetary disk. Most of the mass gathered at the center. Pressure and temperature rose. The central object became a protod, not yet the stable sun we know, but a young body contracting under gravity and surrounded by a disk of leftover material. Within that disk, tiny solid grains collided and sometimes stuck together. Over long periods, some became larger aggregates. Those became planetesimals, bodies large enough for their gravity to become increasingly important. Collisions joined some objects and shattered others. Growing whirls disturbed the material around them. Orbits changed, regions cleared. Some bodies were absorbed, some were broken apart, and some were thrown towards distant frontiers or out of the system entirely. The familiar phrase, "the planets formed from dust," is true, but it can sound gentler than the process really was. Accretion was not the quiet settling of powder. It was a long transformation driven by gravity, heat, repeated impacts, and competition for material. The temperature of the disk helped determine what could form in different regions. In the young sun, it was too warm for many volatile substances to remain frozen. Rock and metal could endure, so the inner planets grew largely from these materials. Farther away, where temperatures were lower, water and other compounds could exist as ice. This made more solid material available for the growth of large planetary cores. Those cores could then gather enormous envelopes of hydrogen and helium, helping to create the giant planets. This gives us the broad architecture still visible today: smaller, rocky worlds close to the sun, followed by giant planets farther out. But it is only a broad outline. Planetary formation was not a neat assembly line in which every object appeared exactly where it now travels. The early planets interacted gravitationally. Models suggest that the giant planets may have shifted their orbits, scattering smaller bodies and altering the architecture of the young system. The details remain an active area of research. Different models attempt to explain the present orbits, the distribution of asteroids and icy objects, and the chemical evidence preserved in meteorites. So the solar system should not be imagined as a finished clock built according to one simple plan. It is a 5-in arrangement. Its present order contains traces of earlier instability. Those traces are found in many places. They appear in the battered surfaces of Mercury and the Moon. They appear in meteorites older than any rock commonly found on Earth's changing surface. They appear in the strange orbits of small bodies beyond Neptune. They appear in the composition of comets, in the tilted rotation of Uranus, and in moons that may have formed beside their planets or been captured much later. Every region preserves a different part of the story. The result is a system of categories that are useful but never perfectly tidy. There are 8 planets. There are dwarf planets, moons, asteroids, comets, and countless smaller objects. Some asteroids have moons. Some dwarf planets have complex satellite systems. Several moons are larger than some recognized planets. Titan has a thick atmosphere. Europa and Enceladus are believed to contain oceans beneath ice. Io is more volcanically active than any other known world in the solar system. A journey concerned only with the 8 planets would therefore miss some of the most revealing destinations. It would also miss the force that connects them. Gravity from the Sun dominates the movement of the solar system. Almost all of the system's mass is concentrated in this single star. The planets are impressive from a human perspective, but together they account for only a small fraction of the whole. This imbalance explains why the Sun is not merely the first object on our route. It is the reason the route exists. The system begins with the star at its center. From Earth, the Sun appears as a smooth disk. Its light is so intense that looking directly at it without proper protection can damage the eyes. Seen through instruments designed for the purpose, it becomes a changing landscape of magnetic fields, bright arcs, dark sunspots, flowing plasma, and enormous eruptions. The Sun is about 4.6 billion years old. It is a main sequence star, composed mainly of hydrogen and helium, with a diameter of roughly 1.4 million kilometers. Around 109 Earths could be placed side by side across that diameter. It contains about 99.8% of the mass of the solar system. That mass creates tremendous gravitational pressure in the core. The temperature there reaches about 15 million degrees Celsius. Under these conditions, hydrogen nuclei can ultimately combine to form helium through a sequence of nuclear reactions. This is nuclear fusion. Fusion is not the same as ordinary burning. A fire rearranges electrons in chemical reactions. The Sun's core changes atomic nuclei. A small amount of mass is converted into energy in accordance with the relationship between mass and energy described by Einstein. The released energy helps support the Sun against its own gravity. Gravity pulls material inward. Pressure associated with a hot interior pushes outward. For most of the Sun's long main sequence life, these influences remain in a changing but remarkably durable balance. The light reaching Earth today began as energy deep inside the core. Its path outward was not direct. Beyond the core lies the radiated zone. Here, energy moves through repeated interactions with matter. A photon can be absorbed and re-emitted many times, changing direction again and again. NASA estimates that energy may take around 170,000 years to travel from the core to the top of this region. Beyond the radiative zone lies the conduction zone. Here, as the plasma rises, transfers energy, cools and sinks again. This motion resembles convection in a heated liquid, although the material in the Sun exists under conditions far removed from an ordinary fluid on Earth. At last, energy reaches the photosphere, the layer usually described as the Sun's visible surface. The word surface is convenient, but the Sun has no solid ground. It is a sphere of plasma held together by gravity. The photosphere is the region from which most visible sunlight escapes into space. Once a photon leaves this layer in the direction of Earth, the final stage of its journey is astonishingly quick. After perhaps thousands of years working outward through the star, it crosses the distance to Earth in a little over 8 minutes. Sunlight carries warmth, but it also carries information. By separating it into a spectrum, scientists can identify chemical elements, measure motion and temperature, and examine magnetic effects. Almost everything known about distant stars relies on learning how to read light in this way. The Sun, close enough to study in extraordinary detail, is the star that teaches us how to understand the others. Above the photosphere lie further layers of atmosphere, including the chromosphere and the corona. The corona becomes visible from Earth during the total solar eclipse, when the bright photosphere is covered by the moon. It appears as a pale extended glow. One of the enduring puzzles of solar physics is that the corona reaches temperatures far higher than the visible surface below it. Magnetic processes are central to the explanation, but researchers continue to investigate exactly how energy is transported and released there. The Sun's magnetic field is not a minor decoration on a calm sphere. The Sun rotates, and because it is not solid, different latitudes rotate at different rates. Its moving, electrically conducting plasma generates complex magnetic behavior. Field lines become stretched and twisted. Sunspots appear where strong magnetic fields affect the flow of heat, making regions look darker than their surroundings, although a sunspot would still be intensely bright if seen alone. Solar activity rises and falls in a cycle of roughly 11 years. Near solar maximum, sunspots and eruptions become more frequent. Near solar minimum, the visible disk may appear quieter. The magnetic cycle is more complicated than a single repeating count, and no two cycles are identical, but the rhythm provides a useful framework for understanding the changing sun. Solar flares release energy through the sun's atmosphere. Coronal mass ejections concern immense clouds of magnetized plasma into space. These events are related, but they are not the same thing, and one does not always accompany the other. When Earth lies in the path of a significant eruption, the effects may arrive as space weather. Earth's magnetic field deflects much of the incoming charged material, but the interaction can disturb the space around the planet. It can intensify auroras, affect radio communication and satellite operations, induce electrical currents, and create increased radiation hazards for spacecraft and astronauts. The same sun that sustains life is therefore also an active part of Earth's environment. Its influence does not stop at light and gravity. From the corona, plasma continually streams outward. This is the solar wind, a thin flow of charged particles carrying magnetic fields away from the sun. It is not wind in the terrestrial sense. There is far too little material for it to feel like moving air. Yet across enormous distances, it shakes planetary magnetospheres, strips particles from unprotected atmospheres, and pushes the ion tails of comets away from the sun. Because the sun rotates while the solar wind travels outward, the magnetic fields carried into space form a vast spiral pattern. It is often called the Parker spiral, after the physicist Eugene Parker, who developed the theory of the solar wind before spacecraft measured it directly. The outward flow inflates the heliosphere, an immense region dominated by the sun's plasma and magnetic influence. Every planet orbits within it. Earth does not merely circle with the sun's light. In this broader sense, it travels inside the sun's extended atmosphere. The heliosphere is not a perfectly round fixed bubble. It changes with solar activity and interacts with the interstellar material through which the solar system moves. Its distant boundaries are regions, not rigid shells. Much later in our journey, the Voyager spacecraft would help us understand those boundaries. Their instruments detected the changing conditions of the solar wind slowed, passed through the heliosheath, and gave way to the environment beyond the heliopause. For now, we remain close to the source. The sunlight is intense, the solar wind is young, the first planetary orbit lies ahead. Mercury is often introduced as a small scorched world little more than a cratered stone beside the sun. But the first planet is more complicated than that description suggests. It is ice in permanent shadow, a metallic core of unusual scale, a global magnetic field, and an orbit with subtle behavior once exposed to limited Newton's description of gravity. To reach it, the two discover that even the nearest planets can resist a simple story. Mercury moves around the sun faster than any other planet. One orbit takes only 88 Earth days. Its path is more elliptical than those of most planets, carrying it between about 47 million and 70 million kilometers from the Sun. Across that changing distance, the sunlight falling upon Mercury varies greatly. The planet also turns very slowly. One rotation relative to the distant stars takes about 59 Earth days, but rotation and daylight are not the same thing. Mercury completes 3 rotations for every 2 journeys around the Sun. Because its orbital motion and its spin are locked in this 3-to-2 relationship, one complete cycle from sunrise to sunrise lasts 176 Earth days. A day on Mercury is therefore longer than the Mercurian year. This produces a sky unlike any experienced on Earth. From certain positions on the surface, the Sun would appear to slow, stop, reverse direction briefly, and then continue. The effect is not caused by the Sun changing its movement. It comes from the combination of Mercury's rotating surface and its changing speed along an elliptical orbit. For a very long time, astronomers thought Mercury might keep one face permanently turned toward the Sun. Radar measurements in the 1960s revealed the true rotation period and its unusual resonance with the orbit. The planet's proximity to the Sun makes it difficult to observe from Earth. Mercury never appears far from the Sun in our sky. It can be glimpsed near the horizon around dawn or dusk, but it does not climb into a dark midnight sky as Mars, Jupiter, and Saturn can. Sending a spacecraft there is also less straightforward than the small distance might suggest. A spacecraft leaving Earth already shares Earth's rapid motion around the Sun. To enter orbit around Mercury, it must lose a great deal of that sideways speed without carrying an impractical amount of fuel. Mission planners use carefully arranged flybys of planets to alter a spacecraft's path and speed through gravity. Mariner 10 became the first spacecraft to visit Mercury when it flew past 3 times in the 1970s. It photographed only part of the surface because the geometry of each encounter brought the same broad region back into sunlight. Decades later, Messenger became the first spacecraft to orbit the planet. Its name was an abbreviation for one from Mercury's surface, space environment, geochemistry, and ranging. Reaching orbit required a journey of more than 6.5 years, including repeated flybys of Earth, Venus, and Mercury itself. Messenger then spent more than 4 years examining the smallest planet. At first glance, Mercury resembles the Moon. Both display ancient surfaces crossed with craters. Both preserve immense impact basins and broad plains shaped by old lava flows. Neither has a thick atmosphere to soften the landscape with rain, rivers, or strong winds. But resemblance is not identity. Mercury is a planet with its own geological history. Its largest well-known impact structure, a caloric basin, stretches roughly 1,500 kilometers across. The impact that formed it sent powerful waves through the planet. On the opposite side, disrupted terrain records the violence of Mercury's early history. Long cliffs called scarps truss parts of the surface, reformed as the planet's interior cooled and contracted, forcing sections of crust over one another. Measurements and images indicate that this contraction was substantial and that some small-scale tectonic activity may have continued far more recently than the oldest landscapes. Messenger also revealed bright, irregular depressions known as hollows. They appear geologically young and may form where volatile material is lost from exposed rock. Their exact history is still studied, but their presence helped replace the image of Mercury as a simple, unchanging relic. Beneath the crust lies one of Mercury's defining features. Its metallic core is enormous, relative to the size of the planet, extending through most of its radius. The reason Mercury ended with so much metal compared with rock is not settled. One family of explanations involves energetic early impacts, stripping away part of an original rocky mantle. Another looks to conditions and processes in the hot inner solar nebula. Measurements of composition and internal structure continue to test these ideas. At least part of the core remains liquid. The motion of electrically conducting material helps generate a global magnetic field. This field is much weaker at the surface than Earth's, but its very existence matters. A small planet should lose internal heat relatively quickly, so an active magnetic dynamo provides clues to the core's composition and cooling history. The field interacts with the solar wind to form a small, changing magnetosphere around Mercury. There is almost no substantial atmosphere. Instead, Mercury is surrounded by an exosphere, an extremely thin collection of atoms released from the surface by sunlight, impacts, and a solar wind. The particles are so sparse that they do not behave like the dense hair of Earth or Venus. They can escape and be replenished, making the space immediately around Mercury part of the planet's continuing story. Without a thick atmosphere to transport and retain heat, surface temperatures reach extremes. Sunlit regions can rise to about 430 degrees Celsius. At night, temperatures can fall to around minus 180 degrees. Yet the innermost planet contains water ice. Mercury's rotational axis is almost upright. At the poles, the floors of some deep craters never receive direct sunlight. These permanently shadowed regions remain cold enough to preserve frozen material. Earth-based radar first detected unusually reflective deposits, and MESSENGER provided evidence that the dominant material in many of them is water ice, sometimes protected beneath a darker insulating layer. This is not a contradiction once temperature is understood locally. Mercury is close to the Sun, but sunlight cannot warm ground it never reaches. The planet does not have one meaningful temperature any more than Earth has one kind of weather. The third world on our route has therefore already unsettled several easy assumptions. The planet closest to the Sun is not the hottest. The nearly airless world can possess ice. The small body that looks ancient can retain a liquid layer in its core and show signs of comparatively recent geological change. We now move outward to the planet that is hotter than Mercury. Venus is often the brightest planet seen from Earth. Beneath a clear horizon, it may appear before sunrise or remain after sunset, brilliant enough to be mistaken for an approaching aircraft. Because it orbits closer to the Sun than Earth does, it never wanders across our entire night sky. It remains tied to the general direction of dawn or dusk. Through a telescope, Venus shows phases. Galileo observed these changing shapes in the early 17th century. Full set of phases made sense of Venus' travel around the Sun, providing powerful evidence against models that placed Earth at the center of every planetary orbit. At visibly wavelengths, the planet itself remains hidden. A continuous deck of pale clouds covers Venus, reflecting much of the sunlight that reaches it. Early telescopes could reveal almost nothing about the ground below. For generations, the concealed surface invited speculation, perhaps a wet jungle beneath endless clouds, perhaps a vast ocean, perhaps a younger version of Earth. Spacecraft replaced those imagined worlds with a far harsher reality. Venus is nearly the same size as Earth. Its diameter is only a little smaller, and its bulk composition is thought to be broadly similar. Both planets formed in the inner solar system from related materials, yet their present surfaces could hardly be more different. The atmosphere of Venus is mostly carbon dioxide. At ground level, its pressure is about 93 times the pressure at sea level on Earth. This is comparable to the pressure beneath roughly 900 meters of water in Earth's oceans. The average surface temperature is about 465 degrees Celsius, 5 degrees Celsius. It changes relatively little between day and night, or between the equator and the poles. Mercury can become hotter at particular sunlit locations, but Venus maintains greater heat across the planet and is therefore the hottest planet overall. The reason is its atmosphere. Sunlight passes through the clouds and atmosphere, although a large portion is reflected back into space. The surface absorbs some of the incoming energy and emits energy at infrared wavelengths. Carbon dioxide and other greenhouse gases absorb and re-emit infrared radiation, making it harder for energy to escape directly to space. The greenhouse effect itself is not unique to Venus, nor is it inherently destructive. It is a physical process operating on Earth as well, where naturally occurring greenhouse gases help keep the surface warm enough for liquid water and life as we know it. On Venus, however, the immense carbon dioxide atmosphere produces an extreme greenhouse state. Models of the planet's evolution suggest that Venus may once have had very different surface conditions. How much water it possessed, how long any temperate period lasted, and exactly how the modern atmosphere developed remains subjects of research. The phrase runaway greenhouse is often used for Venus. In its strict scientific sense, it describes a feedback in which warming allows more water vapor to enter the atmosphere, further strengthening heat retention until surface water can be lost. The modern planet is the end result of a long history, not a demonstration that distance from the Sun alone determines the world's fate. High above the surface are clouds containing droplets of sulfuric acid. The upper atmosphere moves around the planet far faster than the solid world rotates below, a pattern called superrotation. Venus itself turns extremely slowly and in the opposite direction from most of the planets. Relative to the distant stars, one rotation takes about 243 Earth days. One orbit around the Sun takes about 225 Earth days. Its rotation is therefore longer than its year. Because of the interaction between this backward spin and the planet's orbital movement, sunrise to sunrise lasts about 117 Earth days. From the surface, if the clouds ever allowed the Sun to be seen clearly, it would rise in the west and set in the east. The origin of the retrograde rotation is uncertain. An early collision may have contributed. The long-term gravitational interactions and atmospheric tides may also have altered the spin. The present motion is a result to explain, not a complete record of how it happened. Reaching the surface has been possible, but surviving there is difficult. The Soviet Venera program achieved the first successful transmissions from the surface of another planet. Its landers returned measurements and, in several cases, images from a landscape of broken rock beneath an orange-tinted sky. Even the longest-lived landers operated for only a little over 2 hours before heat and pressure ended their work. Orbiters can study Venus for much longer, but visible light cameras cannot simply photograph the hidden ground. Radar provides another way. Radio waves can pass through the clouds, strike to the surface, and return information about roughness, elevation, and structure. During the early 1990s, NASA's Magellan spacecraft used radar to map almost the entire planet at far greater detail than had previously been possible. The resulting landscape is dominated by volcanism. Venus's broad volcanic plains, immense shield volcanoes, long lava channels, deformed mountain belts, and unusual circular structures called coronae. There are relatively few impact craters, and they are spread across the surface in a way that suggests much of the visible crust is geologically younger than the oldest surfaces of Mercury, Mars, or the Moon. Scientists once debated whether Venus had experienced a short, nearly global episode of resurfacing. The modern picture is more complicated. Different regions may have been renewed at different times, and analysis of old Magellan radar observations has provided evidence consistent with volcanic changes occurring during the spacecraft's own mission. Venus appears to be active, but it does not display Earth's familiar system of moving tectonic plates. Its crust may deform through other processes, including localized regions where surface material is stretched, compressed, or driven downward. Researchers use radar, gravity measurements, laboratory work, and computer models to understand how the planet releases internal heat. Venus also lacks an internally generated global magnetic field like Earth's. The solar wind interacts directly with its upper atmosphere and creates an induced magnetic region. Over time, solar radiation and charged particles can help move atmospheric material to space. This does not mean the solar wind alone turned Venus into its modern form. Atmospheric evolution depends on many connected factors: initial composition, volcanic gases, water, surface chemistry, impacts, internal activity, and distance from the Sun. Planetary history is rarely reduced to one cause. Mercury and Venus are neighbors in the inner solar system, but they respond to sunlight in opposite ways. Mercury's thin exosphere stores almost no heat, allowing severe differences between light and darkness. Venus's enormous atmosphere moves heat around the entire planet and prevents the surface from cooling at night. One has exposed craters and ice hidden in shadow. The other has clouds that conceal volcanic plains beneath crushing carbon dioxide. Distance matters, but it does not act alone. This becomes clearer as we approach the third planet. Earth can be difficult to describe objectively because every familiar landscape belongs to it. Mountains, oceans, weather, soil, and life do not seem like planetary features when they form the background of ordinary experience. Seen from space, the categories change. Earth is a rocky world with a radius of about 6,371 kilometers. It travels at one astronomical unit from the Sun by definition, though its actual distance changes modestly along its orbit. One revolution takes about 365.25 days. One rotation relative to the Sun produces the cycle we call a day. Its most visible feature is water. The global ocean covers about 71% of the surface. Water also circulates through the atmosphere, ice, soil, rock, and living organisms. It evaporates, condenses, falls as rain or snow, flows through rivers, freezes into glaciers, enters the ground, and returns to the sea. This water cycle is connected to the atmosphere, the climate, and the continual alteration of the solid planet. The atmosphere near the surface is about 78% nitrogen and 21% oxygen, with the remaining fraction made from argon, carbon dioxide, water vapor, and other gases in varying amounts. These numbers are not merely ingredients in a container. The atmosphere is active. It moves energy and water around the globe, produces weather, filters harmful radiation, and causes most incoming meteoroids to burn before reaching the ground. Its composition has also changed profoundly through geological time. The oxygen now present in such abundance was not simply delivered by the young planet in its modern form. Life altered the atmosphere, while the atmosphere and oceans altered the possibilities for life. Earth is a system in which geology, chemistry, and biology have influenced one another for billions of years. The solid surface changes as well. Earth's outer rocky layer is divided into tectonic plates. These move slowly over the underlying mantle, generally at rates comparable to the growth of fingernails. Where plates separate, a new crust can form. Where they converge, one plate may descend beneath another. Mountains may rise, and earthquakes and volcanoes may follow. Over immense periods, ocean basins open and close while continents assemble and break apart. Plate tectonics continually renews much of Earth's surface. This is one reason very ancient impact scars are harder to preserve here than on the Moon or Mercury. Weathering, erosion, sediment, volcanism, and life further rewrite the landscape. The planet also possesses a global magnetic field generated by motion within its electrically conducting outer core. The solar wind distorts this field into a magnetosphere, extending far into space on Earth's night side. It helps deflect charged particles, though the relationship between magnetic fields and long-term atmospheric protection is more complicated than a simple shield metaphor suggests. Some solar particles become guided into the upper atmosphere near the magnetic poles. There, collisions with atoms and molecules produce the shifting light of auroras, which on the surface an aurora can appear as a curtain across the sky. From a planetary perspective, it is evidence of the conversation between Earth and its star. The sun supplies energy, the atmosphere and ocean distribute it. The solid Earth releases heat from within. The magnetic field meets the solar wind. And throughout these overlapping systems, life has become a geological and atmospheric influence of its own. Earth is the only world currently known to be inhabited. The word known is essential. It states the evidence without claiming that life exists nowhere else. No confirmed detection has yet established life beyond Earth, but many environments in the solar system are studied because they contain some of the conditions life may require. Our home is not alone. Decide it traveled a companion large enough to influence oceans, preserve the early history of both worlds, and make the Earth-Moon system distinctive among the inner planets. To understand Earth from outside, we must now turn toward the Moon. The Moon is close enough to reveal detail with the unaided eye. Its darker patches form broad shapes that people have interpreted as faces, animals, and figures. These regions were once called Madia, the Latin word for seas, because early observers imagined they might contain water. They are not seas. They are plains of ancient basalt created when lava rose through fractures and filled enormous impact basins. The lighter regions are older, heavily cratered highlands. From Earth, this landscape appears almost timeless. There are no clouds moving across it, no rivers cutting new channels, no vegetation changing with the seasons. Yet the Moon is not untouched. Small objects continue to strike its surface. Temperature rises and falls through the long lunar day and night. The crust contracts as the interior slowly cools. Dust is continually disturbed by radiation and impacts. The absence of a thick atmosphere means that evidence can remain visible for immense periods. A footprint, a crater, and a lava plain belong to completely different scales of time, but all can persist because there is little air or liquid water to erase them. This makes the Moon an archive. Its rocks preserve evidence from the early solar system that Earth's active surface is largely destroyed or transformed. Samples returned by the Apollo missions help scientists establish the ages and origins of lunar terrains. They also strengthen the leading explanation for how the Moon formed. According to the broad giant impact model, the young Earth was struck by a large planetary body about 4.5 billion years ago. Material from Earth and the impact entered into orbit, where it gathered to form the Moon. A hypothetical impactor is often called Thea. This account explains several important observations, including the Moon's relatively small metallic core and the close chemical relationship between lunar rocks and Earth's mantle. But the details are not settled. Models must explain the composition of samples, the Moon's present orbit, the angular momentum of the Earth-Moon system, and the differences between the lunar, near, and far sides. Some simulations produced the Moon rapidly after one immense collision. Other versions involve different impact conditions or more than one event. The evidence strongly favors an energetic origin connected to the young Earth, while leaving room for scientific disagreement about exactly how it unfolded. The newly formed Moon was far closer to Earth than it is today. Much of it was molten, producing a global or nearly global ocean of magma. As it's cooled, lighter minerals rose and helped form the early crust. Later impact sets created basins and volcanic activity filled many of them with dark rock. The difference between the near and far side is striking. The familiar face turned toward Earth contains extensive dark plains. The far side has a thicker crust and far fewer of these basaltic maria. It's not permanently dark. It experiences daylight and night like the near side. The name dark side is therefore misleading when it is used to mean a place without sunlight. We see one face because the Moon rotates at the same rate that it orbits Earth. This is synchronous rotation produced over time by tidal interaction. Early in its history, the Moon rotated more quickly. Earth's gravity raised a slight distortion in the Moon. Because the Moon was turning, that tidal distortion did not align perfectly with Earth. The resulting gravitational forces gradually reduced the rotation until one spin maxed one orbit. The Moon still rotates. If it did not, observers on Earth would eventually see every side as it completed an orbit. Instead, it turns once during its journey, continually presenting approximately the same hemisphere toward us. Approximately is important because the orbit and viewing geometry allow a gentle, apparent rocking called libration. Over time, observers from Earth can see a little more than half of the lunar surface, but the far side remained largely unknown until spacecraft traveled around it. Tides connect the two worlds in the present as well as the past. The Moon's gravity acts more strongly on the side of Earth nearer to it than on the side farther away. Along with the motion of the Earth-Moon system, this helps produce tidal bulges. Earth's rotation carries coastlines through the changing distribution of ocean water, while continents, seafloor shape, Weather and local geography determine the tides actually experienced at a particular shore. The sun contributes too. When the sun, earth and moon are aligned, their tidal influences reinforce one another, creating spring tides. When the sun and moon lie at right angles as viewed from Earth, the difference between high and low tide is generally reduced, producing neap tides. Friction within Earth's oceans and solid body transforms some rotational energy into heat. The tidal bulges are carried slightly ahead of the moon, and their gravitational attraction gives energy to the moon's orbit. As a result, the moon is slowly moving away from Earth at about 4 centimeters per year, while Earth's rotation is gradually slowing. These changes are tiny on a human timescale, but over geological time they alter the distance between the worlds and the length of Earth's stay. The moon may also have influenced the long-term behavior of Earth's rotational axis. It is often said simply that the moon stabilizes Earth's tilt. The underlying dynamics are more complicated, and Earth's axis still changes. A safer conclusion is that large companion has played an important part in the rotational history of our planet. At an average distance of about 384,000 kilometers, the moon is the most distant place humans have visited in person. It is also the first other world whose surface people learned to recognize through direct experience. The grey ground of Apollo photographs is covered by regolith, a layer of fragmented rock and fine dust produced by impacts. With no weather in the terrestrial sense, sharp grains are not rounded by flowing water or wind. The horizon can appear strangely near because the moon is smaller than Earth, and because the clear, airless view lacks familiar atmospheric haze. Water nevertheless exists there. Ice is preserved in permanently shadowed polar regions, and water molecules have also been detected in sunlit material. This does not imply lunar lakes or damp soil. The amounts, physical forms, and accessibility vary. The discoveries matter both as evidence about how water moves through the solar system and as a possible resource for future exploration. Seen together, Earth and Moon form a coupled system. The Moon records the violence of their early formation. Its gravity moves Earth's oceans and has gradually changed the rotation of both bodies. Earth illuminates the lunar night, while the Moon periodically crosses the Sun or passes into Earth's shadow. From farther away, their differences become even more striking. One world has a shifting atmosphere, oceans, active plate tectonics, and a biosphere. The other has an airless surface that preserves events billions of years old. They formed from connected material and have traveled together ever since, yet their later history is separated almost completely. Beyond the Earth-Moon system lies another rocky world where the past is written across the ground. Mars is farther from the Sun, smaller than Earth and now cold and dry. But its empty channels, over minerals and layered sediments reveal that the planet visible today is not the planet that always existed. Mars has invited imagined journeys for centuries. Its reddish light is visible without a telescope. As Earth and Mars move around the Sun, the distance between them changes enormously. At favorable times, Mars becomes bright and its surface features can be followed through telescopes. At other times, it lies far across the solar system, and radio signals may take many minutes to travel each way. This changing distance shapes every robotic mission. Commands cannot control the lander in real time during descent. A spacecraft must carry instructions, assess parts of the situation itself, and act before news of an error could even reach Earth. Mars takes about 687 Earth days to orbit the Sun. Its day quarter soil lasts approximately 24 hours and 39 minutes. This near match with Earth's day has made the rhythm of surface missions feel oddly familiar. Teams operating rovers have sometimes organized their working lives around Martian time, allowing their own schedules to drift through the terrestrial day. The planet's axis is tilted by about 25 degrees, similar to Earth's tilt. Mars therefore has seasons. Its orbit is more elliptical than Earth, so distance from the Sun also affects the strength and duration of those seasons. Because a Martian year is almost twice as long, the seasons last longer. The southern hemisphere experiences shorter, warmer summers near the planet's closest approach to the Sun, while northern seasons follow a different rhythm. Polar caps grow and retreat. They contain water ice, but seasonal carbon dioxide frost also freezes from the atmosphere during winter and returns to gas as sunlight increases. These exchanges alter atmospheric pressure across the year and help drive Martian weather. The atmosphere is mostly carbon dioxide, with nitrogen and argon among its other components. Its pressure at the surface is less than 1% of Earth's average sea level pressure, though elevation causes significant local differences. The air is thick enough to produce clouds, wind, dust devils, and immense dust storms. It is far too thin to retain heat as Earth's atmosphere does. Temperatures vary sharply with place, season, and time of day. Dust gives the sky its color. Fine particles rich in iron minerals are lifted into the air and spread across the ground. From the surface, daylight usually passes through a butterscotch or reddish haze. Around sunset, the sky near the sun can appear blue because the fine dust scatters light differently from molecules in Earth's atmosphere. The same dust settles on solar panels, coats instruments, and traces the movement of wind. Sometimes a passing dust devil cleans the spacecraft unexpectedly. Sometimes a global storm looks so much sunlight that a solar-powered mission can no longer continue. The Martian landscape contains extremes. Olympus Mons is the largest known volcano in the solar system. It rises gradually across a base hundreds of kilometers wide. Its height was made possible in part because Mars lacks active plate tectonics like Earth's. A volcanic source could remain beneath broadly the same region of crust, building layer upon layer instead of being carried away by a moving plate. Across another part of the planet stretches Valles Marineris, a system of canyons thousands of kilometers long. It is sometimes called the Grand Canyon of Mars, but the comparison can conceal more than it explains. Valles Marineris is vastly larger, and much of it formed through tectonic stretching and collapse, later modified by landslides, erosion, and perhaps water. The northern and southern hemispheres also differ. Much of the north consists of lower, smoother plains. The south contains older, more heavily cratered highlands. The origin of this global contrast may involve internal processes, immense impacts, or a combination of events. All of these features make Mars geologically rich. The most persistent question follows water. Orbital images show branching valley networks resembling drainage systems. There are channels carved by enormous floods, fan-shaped deposits and deltas where rivers once entered standing bodies of water. Others have examined rounded pebbles transported by flowing water and sediments laid down in ancient lakes. Minerals provide another line of evidence. Clays in certain sulfates form or alter in the presence of water. Their distribution recount environments that change through time. Some ancient terrain suggests water with conditions that may have been comparatively mild. Lighter deposits can reflect more acidic or evaporating environments. Yale crater, explored by the Curiosity rover, once held lakes. Layers in and around Mount Sharp preserved changing conditions over a long period. Jezero crater, explored by Perseverance, contains an ancient river delta where water carried sediment into a lake. These sites were not selected because they prove life existed. They were selected because water, sediment, and chemical energy can create and preserve environments relevant to habitability. Habitability means that an environment may have possessed conditions compatible with life as we understand it. It is not the same as habitation. A lake can be potentially habitable without ever containing an organism. No mission has confirmed past or present life on Mars. This distinction matters because the search operates through several layers of evidence. A rover can establish that liquid water existed. It can identify organic molecules, meaning carbon-containing compounds. It can examine textures and chemical patterns that deserve further study. None of these observations alone establishes a biological origin. Organic chemistry is not exclusive to life. Carbon compounds can form through non-biological processes and can arrive on meteorites. A convincing detection of ancient life would require evidence that survives careful attempts to explain it in other ways. The water story also asks what happened to the planet as a whole. Ancient rivers and lakes require surface conditions different from those prevailing today. Liquid water cannot remain stable for long across most of the modern surface because the atmosphere is cold and thin. Early Mars must therefore have had periods when pressure, temperature, and the supply of water allowed lakes and flowing rivers to persist. Mars was never simply a smaller Earth. Models still struggle to explain how a relatively faint young sun and the ancient Martian atmosphere produced all of the environments recorded in the rocks. Warm intervals may have alternated with colder conditions. Impacts, volcanism, clouds, and atmospheric chemistry may all have contributed. Over time, a large part of the atmosphere was lost or locked into the surface. Mars has no strong global magnetic field today, although magnetized regions in ancient crusts show that it once generated one. As the interior cooled and the global dynamo faded, the upper atmosphere became more directly exposed to solar radiation and the solar wind. NASA's MAVEN mission, whose name stands for Mars Atmosphere and Volatile Evolution, spent more than 11 years studying the upper atmosphere and its interaction with the Sun. Its observations help measure processes that move atmospheric particles to space. One such process is sputtering. Incoming charged particles can transfer energy through the upper atmosphere, ultimately knocking other atoms away. In 2025, scientists reported MAVEN's first direct observation of this elusive process at Mars, strengthening evidence that it played an important role when the young sun was more active. Atmospheric escape is not the only destination for ancient Martian water. Some water became chemically bound in minerals. Large quantities remained frozen in the polar caps and beneath the surface at high and middle latitudes. Radar, neutron measurements, give a size and landform shaped by past glaciation reveal a planet where water is still present, but commonly hidden or frozen. Claims of present liquid water require particular care. Dark streaks that appear seasonally unsloped were once widely described as possible briny flows. Later evidence showed that many can be explained by dry grains moving downhill. Extremely salty liquid may occur briefly under unusual local conditions, and deep subsurface reservoirs have been proposed. But stable pools across the exposed surface are not part of the modern Martian landscape. The progression of Mars exploration reflects this growing caution. Early flybys established a cratered world with a thin atmosphere. Orbiters revealed volcanoes, canyons, and channels. Viking landers carried biological experiments whose results proved difficult to interpret and did not establish life. Later missions followed the history of water. Rovers became field geologists, reading layers, drilling rocks, and choosing routes through ancient environments. Each generation replaced a simple Mars with a more complicated one. The planet is neither the dying civilization imagined in early fiction nor a completely inert desert. It has weather, frost, moving dunes, avalanches, Marsquakes, and a geological record shaped by water, ice, lava, and impact. Mars has two small moons, Phobos and Deimos. Both are dark, irregular, and heavily cratered. Their origins remain debated. They may be captured objects, but their nearly circular equatorial orbits have also encouraged models in which debris around Mars gathered into moons after an impact. Phobos is the larger and closer of the two. It races around Mars roughly 3 times each Martian day. Tidal interaction is drawing it slowly inward. In tens of millions of years it may strike Mars or be torn apart to form a ring. Deimos orbits farther away and takes about 30 hours to complete one journey. From the Martian surface near the moon would resemble Earth's large lunar disk. Phobos can cross the Sun but is too small to cover it completely, producing a rapid, irregular transit rather than a total eclipse like those sometimes seen from Earth. As we leave Mars, the neat division between planets and debris begins to weaken. Ahead lies a region often depicted as a dangerous field of crowded rocks. In reality, its objects are separated by enormous distances. Spacecraft cross it routinely without weaving between boulders. Yet the apparent gap between Mars and Jupiter is scientifically clouded. It contains fragments of early planetary history, a dwarf planet with bright salt deposits, families born from collisions, and objects whose paths sometimes approach Earth. The next stage of the journey belongs to the small worlds. The asteroid belt is not the remains of a single planet that exploded, nor is it a densely packed barrier through which a spacecraft must steer every few seconds. Most of its objects travel in the broad region between Mars and Jupiter. Even there, the distances between substantial bodies are usually enormous. A person standing on one asteroid would not normally see a neighboring asteroid filling the sky. They would see darkness, the distant sun, and with sufficient equipment, points of light moving against the stars. The crowded belt of cinema belongs more to adventure than astronomy. This does not make the real region empty or unimportant. It contains millions of bodies large enough to be treks, along with countless smaller fragments and dust grains. Their combined mass, however, is less than the mass of Earth's moon. The belt is not one uniform ring. Its occupants travel on different orbits with different tilts and degrees of elongation. Some are isolated remnants. Others belong to families whose related parts and compositions reveal that they were created when a larger parent body was broken apart. There are also gaps where relatively few asteroids remain. These are not empty because unseen planets create a physical lane through the belt. Many arise from orbital resonances with Jupiter. If an asteroid completes a simple number of orbits for every orbit of Jupiter, repeated gravitational tugs can accumulate. Over time, its orbit may become unstable and move away from that region. Jupiter's influence is therefore present long before we reach the giant planet itself. It helps shape the belt, but the familiar statement that Jupiter's own prevent us of planet from forming there is too simple. The early region was affected by the distribution of material, collisions, gas, the growth and migration of planets, and changing gravitational resonances. Modern models attempt to reconstruct that history from the belt we see now. Rather than a failed planet, it is better to imagine a population of survivors. Some preserve primitive material little changed since the early solar system. Others are fragments of bodies that once melted, separated into layers and developed crusts and metallic interiors. The word asteroid therefore describes an orbital population more readily than one kind of rock. Broad compositional groups include dark carbon-rich objects, stony asteroids dominated by silicate materials, and bodies containing substantial metal. These classifications are useful, but real objects do not always fit perfectly into three boxes. Their histories depend partly on size and early heating. Short-lived radioactive elements generated heat in the young solar system. A sufficiently large body that formed early could melt internally. Dense metal sank toward the center, while lighter rock rose above it. Later collisions could expose or scatter those layers. A metallic asteroid may therefore represent material once buried inside a larger object. A basaltic fragment may come from an ancient rust. A dark, primitive body may preserve water-bearing minerals and carbon compounds from a colder region of the early disk. Vesta provides one of the clearest examples of a small world with a complex interior. It is the second largest body in the main belt after Ceres and has a differentiated structure with a crust, mantle, and core. An immense impact near its south pole excavated a basin hundreds of kilometers across and sent fragments into space. Some of those fragments eventually reached Earth. Scientists can connect a family of meteorites with Vesta by comparing their composition and spectra with observations of the asteroid. These rocks allow laboratories on Earth to study material from a known distant world without sending a sample return mission there. The language of small bodies can become confusing because a single piece of material receives different names during its journey. An asteroid is generally a larger rocky or metallic object orbiting the Sun. A meteoroid is a much smaller natural object in space. When a meteoroid enters an atmosphere and produces a luminous trail, the light is called a meteor. If part of the object survives to reach the ground, that surviving piece is a meteorite. The bright streak is not simply a rock blown because it rubs against air like a hand against cloth. At high speed, the object compresses the air before it. Gas heats, material melts or vaporizes, and ionized atoms produce light. Small particles often disappear completely. Larger or stronger fragments may slow enough for surviving pieces to fall to the ground. Meteorites are physical records of planetary formation. Some contain tiny inclusions among the oldest solid materials dated in the solar system. Some preserve evidence of water altering their parent bodies. Iron meteorites can sample the cores of objects long since destroyed. Others are pieces blasted from the Moon or Mars by impacts powerful enough to lift rock beyond those worlds' gravity. The belt can therefore be studied from telescopes, spacecrafts, and fragments delivered naturally to Earth. NASA's Dawn mission added a particularly revealing perspective. Dawn was the first spacecraft to orbit 2 worlds beyond Earth. It traveled first to Vesta and later to Ceres, using an ion propulsion system that produced a gentle but persistent thrust over long periods. The 2 destinations offered a comparison between neighboring bodies that had followed different paths. Vesta is dry, rocky, and shaped by early melting and immense collisions. Ceres is darker, rounder, and rich in water-bearing material. Ceres was discovered in 1801 by Giuseppe Piazzi. It was first announced as a planet. As more bodies were found in similar orbits, it became part of the newly recognized asteroid population. In 2006, it was classified as a dwarf planet. That changing label did not alter Ceres itself. It reflected changing knowledge and the need to organize a growing variety of worlds. At roughly 940 kilometers across, Ceres is large enough for its gravity to have pulled it into an approximately spherical shape. It contains a substantial portion of the entire belt's mass, though published estimates differ depending on the adopted measurements. Before Dawn arrived, Ceres appeared as little more than a blurred disk. The spacecraft revealed a cratered landscape marked by landslides, fractures, a solitary mountain, and hundreds of bright deposits. The brightest lie within the Kuiper crater. At first, images showed points so reflexive that they appeared almost white against the dark ground. Higher resolution observations revealed deposits rich in sodium carbonate and other salts. The salts point toward a history involving briny liquid beneath the surface. Ceres contains abundant water ice, although it does not possess a global surface ocean. The impact's heating, fractures, and dissolved salts can allow liquid to persist or move under conditions where pure water would freeze. Evidence from Dawn indicates that material from below reached the surface in the geologically recent past. Ahona Mons, rising several kilometers above the surrounding terrain, is interpreted as a cryovolcano. Instead of erupting molten silicate rock like a terrestrial volcano, it was built from colder material involving water, salts, and mud-like mixtures. The term cryovolcano should not suggest a mountain spraying loose snow. It describes the movement and eruption of volatile rich material on a cold world. Ceres may still retain pockets of brine below its crust. That does not establish an underground ecosystem, and there was no evidence that Ceres is inhabited. It does demonstrate that small, cold bodies can sustain chemical and geological activity longer than their appearance might imply. The dwarf planet also contains ammonia-bearing minerals. Because ammonia is more stable in colder regions farther from the sun, their presence raises questions about where Ceres formed or how material moved through the early solar system. Once again, the present orbit does not necessarily reveal an object's complete birthplace. Other small bodies travel far beyond the main belt. Some share a planet's orbit around stable regions associated with the Lagrange points. These are called Trojan asteroids. Jupiter has a particularly large Trojan population traveling ahead of and behind it. Mars and Neptune also have Trojans, and a small number associated with Earth. Some asteroids occupy that bring them into the neighborhood of Earth's orbit. They are called near-Earth objects when they meet defined orbital criteria. Near does not mean that an impact is imminent. An object can be placed in the potentially hazardous category because of its size and the geometry of its orbit while having no clear collision with Earth. The classification identifies bodies that deserve careful tracking. Observatories make repeated measurements and specialists calculate how uncertainty in an orbit changes as more data arrive. This work is quiet by design. The goal is to discover objects early, refine their paths, and avoid confusing a possible approach with a confirmed threat. Impacts are part of Earth's history. Small material enters the atmosphere every day, usually without harm. Large impacts are much rarer, but their potential consequences justify systematic observation and research into ways an orbit might be altered if a genuine future threat were found. The boundary between asteroid and comet is also less rigid than it once appeared. Traditionally, asteroids were described as rocky objects and comets as icy bodies that became active near the Sun. This remains useful, but scientists have found objects that complicate the division. Some asteroid-like bodies show cometary activity. Some comets become dormant after losing easily vaporized material and can resemble dark asteroids. A comet is often almost invisible when it is far from the Sun. At its center is a nucleus made from ice, dust, rock, and organic material. Nuclei are commonly dark because their surfaces contain carbon-rich compounds and have been altered by repeated exposure to space. As a comet approaches the Sun, its surface warms. Ice changes directly from solid to gas in a process called sublimation. Escaping gas lifts dust and forms a surrounding cloud called the coma. The coma can grow far larger than the nucleus. Sunlight and the solar wind then shape material into tails. The dust tail is pushed by the pressure of sunlight and tends to curve along the comet's orbit. The ion tail is formed from electrically charged gas carried more directly away from the Sun by the solar wind and its magnetic field. A comet's tails therefore point broadly away from the Sun, not necessarily behind the comet's direction of travel. On the outward part of an orbit, the comet can move away from the Sun while its tails extend in front of its motion. The familiar image of a tail streaming behind like hair in the wind is not always correct. Repeated visits to the inner solar system gradually alter a comet. Jets can reshape its surface. Dust can settle back. Ice is lost. The nucleus may split into pieces or become inactive. Short-period comets commonly trace their origins to icy populations beyond Neptune. Long-period comets arrive from much farther away, from the distant reservoir known as the Oort Cloud. Their orbits can be changed by the giant planets, and, in the far outer system, by passing stars and the gravitational tide of the Milky Way. A body preserved in cold darkness for billions of years can therefore be redirected toward the Sun. Comets contain ancient material, but ancient does not mean completely unaltered. They have experienced radiation, impacts, heating, and repeated activity. Spacecraft observations and return dust samples help scientists separate original ingredients from later change. The question of whether comets delivered Earth's oceans has no one-word answer. Impacts by comets and water-rich asteroids probably contributed volatile material to the early Earth, but measurements of hydrogen isotopes show that different comets contain water with different signatures, and many do not match Earth's oceans closely. Earth's water history may include material retained during formation, delivery from several populations, and recycling between the surface and interior. Small bodies do not offer a single origin story, never by pieces of one. As we cross the broad asteroid region, the Sun becomes less intense. At Ceres, night is only a fraction as strong as it is at Earth. Beyond the belt, one object begins to dominate the gravitational landscape. Jupiter is more massive than every other planet combined. It did not become a star, and describing it as a failed star can be misleading. Jupiter and the Sun both contain large amounts of hydrogen and helium, but Jupiter would need vastly more mass for sustained hydrogen fusion to begin in its core. It formed as a planet within the Sun's surrounding disk and remains one, however imposing its scale. Its mass has shaped the paths of asteroids, comets, and spacecraft. It helped organize the early solar system and continues to redirect small objects. Sometimes it sends a body outward that captures it temporarily. Sometimes it alters an orbit toward the inner planets. Calling Jupiter Earth's shield therefore oversimplifies a complicated gravitational role. Jupiter can remove potential impactors from one path or directing other objects into new ones. From a distance, the planet appears as a striped sphere. Light zones and darker belts run parallel to the equator. They are cloud systems carried by powerful eastward and westward jet streams. The colors arrive from chemistry and from material rising and sinking through different atmospheric conditions, though the exact compounds producing every shade remain under investigation. The upper visible clouds contain ammonia ice. Deeper layers are thought to include ammonium hydrosulfide and water clouds, but no spacecraft has descended through the entire atmosphere. In 1995, A probe released by the Galileo spacecraft entered Jupiter and transmitted measurements for less than an hour before pressure and temperature overwhelmed it. The probe entered in an unusually dry region, demonstrating one of the difficulties of sampling a world through a single narrow path. Jupiter has no solid surface in the everyday sense. A descending craft would pass through gas that gradually becomes hotter, denser, and more compressed. There is no clean boundary at which atmosphere suddenly becomes ground. Far below the visible clouds, hydrogen enters fluid states unlike those encountered at Earth's surface. Under immense pressure, electrons can move freely through compressed hydrogen, producing metallic hydrogen. This electrically conducting layer helps generate Jupiter's powerful magnetic field. The deepest interior remains a subject of modeling and measurement. Earlier pictures often showed a small, compact core beneath sharply separated layers. Gravity data from NASA's Juno spacecraft support a more complex structure, possibly including a diluted or fuzzy core where heavy elements are spread through a broad region rather than confined to a simple solid ball. Such measurements matter because the internal distribution of heavy material preserves clues to how Jupiter formed and whether early collisions altered it. The planet radiates more energy than it receives from the Sun. Some comes from slow gravitational contraction and the gradual settling and separation of material inside it. Jupiter is not producing energy by sustained fusion, but it is still cooling from its formation. Its atmosphere moves at extraordinary speed. One rotation takes roughly 10 hours, with the exact period depending on what is measured, because the visible atmosphere does not turn as a rigid surface. This rapid spin makes Jupiter bulge the equator and flatten at the poles. It also organizes the atmosphere into bands and helps maintain enormous storms. The Great Red Spot is a vast anticyclonic storm observed continuously for well over a century, with earlier sightings that may refer to the same feature. It has changed in size, shape, and color. Although it was once wide enough to contain several Earths side by side, it has been shrinking over long-term observations. There is no final explanation for its color or its exceptional longevity. Its depth, surrounding jet streams, and transfer of energy from smaller storms all appear relevant. Juno has shown that Jupiter's bands and storms are not a thin painted layer. The jet streams descend thousands of kilometers below the visible cloud tops before their organized flow weakens. At the poles, the atmosphere forms patterns unlike the familiar horizontal bands. Juno revealed clusters of enormous cyclones arranged around central polar storms. They remain in surprisingly stable geometric groups, while their edges continually interact. Lightning flashes within deep clouds. Auroras glow around the poles. Charged particles move through a magnetic environment of astonishing scale. Jupiter's magnetosphere expands millions of kilometers toward the Sun, and trails far beyond the planet on the night side. It traps and accelerates particles into intense radiation belts capable of damaging spacecraft electronics. Some of those particles come from the solar wind. A major supply also comes from within the Jupiter system, from a small moon whose volcanoes continually release material into space. Jupiter is surrounded by faint rings and a large family of moons. 4 of those moons are so substantial and distinctive that they transform the planet from one destination into a system of worlds. Io is volcanic. Europa hides a global ocean beneath ice. Ganymede is larger than Mercury and produces its own magnetic field. Callisto preserves an ancient, heavily cratered surface. Their different histories are connected by Jupiter's gravity. To understand the giant planet fully, we must leave its clouds for a time and travel among the moons. The 4 large moons of Jupiter were first recognized in January of 1610. Galileo Galilei had turned a newly improved telescope toward Jupiter and noticed small points of light nearby. Over successive nights, the points changed position. Sometimes one disappeared, only to return on the other side of the planets. They were not fixed stars, they were objects traveling around Jupiter. This observation did not by itself prove every part of the Sun's entered mortal, but it delivered a serious blow to the idea that all heavenly bodies must orbit Earth. Here was a center of motion plainly located elsewhere. The moons are now called Io, Europa, Ganymede, and Callisto. Together they are known as the Galilean moons. Through Galileo's small telescope they were moving lights. Modern spacecraft have revealed 4 worlds with different surfaces, interiors, and levels of activity. Their arrangement offers a smaller echo of planetary formation. They're probably assembled from a disk of material around the young Jupiter. The inner moon Io is dominated by rock and metal. Farther out, border ice becomes increasingly important, yet their present condition is controlled by more than composition distance. Gravity continually transfers energy through the system. Io, Europa, and Ganymede participate in an orbital relationship called the Laplace resonance. For every orbit completed by Ganymede, Europa completes approximately 2 and Io completes approximately 4. The moons repeatedly return to related positions, giving one another small but persistent gravitational tugs. Without these interactions, tidal forces would tend to make the orbits increasingly circular. The resonance maintains slight orbital eccentricities. Their distances from Jupiter therefore change as they travel. Jupiter's gravity is stronger on the side of a moon facing the planet than on the side facing away. As the distance varies, the size and direction of this tidal distortion also vary. The moon is repeatedly stretched and relaxed. Rock and ice resist that movement. Internal friction transforms orbital energy into heat. On Io, the result is extreme. Io is slightly larger than Earth's moon and is the most volcanically active world known. Its surface is colored yellow, orange, white, red, and black by sulfur compounds, silicate lava, and changing volcanic deposits. When Voyager 1 passed through the Jupiter system in 1979, navigation engineer Linda Morabito noticed an unexpected plume rising above Io's edge in an image. It was the first active volcanic eruption discovered beyond Earth. Later missions found the world continually resurfaced. Hundreds of volcanic centers mark Io. Some release plumes that rise hundreds of kilometers. Lava lakes expose intense heat. Vast flows spread across the ground, covering all terrain so effectively that few impact craters remain visible. Earth's volcanoes are now powered mainly by leftover heat from formation or radioactive decay, though those sources may contribute. The dominant supply comes from tides. As the solid body fluxes, internal rock is heated and partly melted. The exact pattern of melting, the thickness of the crust, and the distribution of magma remain active questions. Measurements suggest a deeply altered interior, but scientists continue to debate whether a global layer of melt exists or whether molten material is distributed in other ways. The surface would be hostile to life as we know it. There is almost no water, temperatures are generally low away from lava, and Jupiter's radiation is intense. A thin atmosphere of sulfur dioxide grows and collapses as material is released, freezes, and is stripped into space. That escaping material affects the entire Jupiter system. Atoms and molecules from Io become electrically charged and form a broad ring of plasma around Jupiter, known as the Io plasma torus. Jupiter's rotating magnetic field sweeps this material along. Electrical currents connect Io with the giant planet, leaving a detectable auroral footprint in Jupiter's upper atmosphere. The small moon is therefore both a volcanic world and a major source of particles within the largest planetary magnetosphere. The next moon outward presents an almost opposite surface. Europa is covered in water ice. From space it appears pale and relatively smooth, crossed by long reddish-brown lines. There are few large impact craters, suggesting that the visible surface is geologically young compared with the ancient crust of Callisto. The lines include ridges, fractures, and broad bands where the crust has been disrupted. Some regions look like pieces of a broken shell that shifted and froze again. They offer evidence that the ice has communicated with warmer material below. Europa's most important feature cannot be seen directly. Multiple lines of evidence indicate a global ocean of salty liquid water beneath the crust. The Galileo spacecraft measured changes in the magnetic environment around Europa. These are best explained by an electrically conducting layer inside the moon, and the salty ocean is the leading interpretation. Surface geology, young terrain, and Europa's response to tides support the same broad picture. The thickness of the ice remains uncertain. Some models allow a comparatively thin shell of regions where the ocean interacts more directly with the surface. Others favor ice tens of kilometers thick with warmer moving ice below a colder rigid layer. The surface may contain pockets of brine, and exchange between the ocean and crust may occur without an open path reaching all the way through. Claims of water vapor plumes above Europa have been reported from telescope observations and reanalysis of spacecraft data. The evidence is intriguing, but intermittent. A plume is not assumed to be present at every time or place. Tidal flexing supplies heat, preventing the entire interior from freezing solid. If Europa's rocky seafloor remains active, water and rock may interact chemically. Hydrothermal processes are one possible source of energy and dissolved material. These conditions make Europa one of the most compelling places to investigate habitability beyond Earth. Potentially habitable does not mean inhabited. No life has been detected on Europa. Scientists do not yet know the ocean's precise composition, its energy budget, or the degree to which useful chemical ingredients circulate through it. The radiation that strikes the surface creates oxidizing compounds, but whether these can travel through the ice and reach the ocean in meaningful quantities is uncertain. The scientific question is therefore not simply whether Europa has water. Evidence for the ocean is strong. The deeper question is whether its water, rock, chemistry, and energy formed an environment capable of supporting biology. Beyond Europa lies the largest moon in the solar system. Ganymede is wider than the planet Mercury, although it contains far less mass because much of it is ice. Its surface combines older dark terrain with younger, brighter regions marked by grooves and ridges. The groove terrain records large-scale deformation. The icy crust was stretched and broken. Perhaps as internal water froze, expanded, and altered the moon's structure. Ganymede is differentiated into layers with a metallic core, rocky mantle, and an outer shell dominated by water and ice. Models suggest that the outer region may contain several layers of liquid water separated by different forms of high-pressure ice. Its ocean may hold more water than all of Earth's surface oceans combined. Quantity alone, however, does not establish habitability. If high-pressure ice separates liquid water from the rocky mantle, chemical exchange with rock may be limited in ways that differ from Europa. Ganymede is also unique among known moons because it generates its own magnetic field. The Galileo spacecraft discovered this field in the 1990s. It indicates motion within a liquid, electrically conducting portion of the metallic core. Ganymede creates a small magnetosphere embedded inside Jupiter's much larger one. The interaction produces auroras around the moon's poles. Their slight rocking as Jupiter's magnetic field changes has provided further evidence for an electrically conducting saltwater ocean beneath the surface. This is a remarkable arrangement. A moon with a metallic dynamo, an internal ocean, an icy crust, and its own magnetic region, all enclosed within the magnetic environment of the planet. The outermost Galilean moon is Callisto. Its surface is dark and extraordinarily cratered. Unlike Europa, it shows little evidence of widespread recent resurfacing. Ancient impacts have accumulated rather than being erased by persistent volcanism or tectonic renewal. The larger structures are multi-ring basins where impact energy produces patterns of concentric fractures across the icy crust. Callisto does not participate in the same strong orbital resonance as the inner three moons. It therefore experiences much less tidal heating. This helps explain why it remained less active and preserved such an old surface. Yet Callisto is not necessarily frozen completely solid. Magnetic observations from Galileo are consistent with a salty liquid layer beneath the surface. Antifreeze compounds such as ammonia could allow water to remain liquid at lower temperatures. The structure and depth of any ocean remain uncertain. Callisto receives less intense radiation than Europa because it orbits farther from Jupiter. That difference has led to occasional discussion of it as a comparatively practical site for distant human exploration. Such proposals remain speculative and do not change its scientific value as a record of the early Jupiter system. The four moons form a progression. Closest to Jupiter, Io is heated into continual volcanism. Europa contains a rocky interior beneath ice and a global ocean. Ganymede is larger and more layered, with its own magnetic field. Callisto remains ancient and heavily cratered, though it too may conceal liquid water. Distance from Jupiter changes the balance between rock, ice, radiation, and tidal heat. It also demonstrates why moons cannot be treated as minor accessories. Around the giant planets, some satellites are geologically active worlds, and several may contain more liquid water than Earth. The Galileo mission transformed this understanding. It arrived at Jupiter in 1995 and became the first spacecraft to orbit the planet. Despite the failure of its main high-gain antenna to open fully, engineers and scientists redesigned software, compressed data, and improved communications with a smaller antenna. For almost 8 years, Galileo observed Jupiter's atmosphere, rings, magnetic environment, and moons. When its propellant was nearly exhausted, controllers deliberately sent it into Jupiter in 2003. The decision prevented an uncontrolled future collision with Europa, preserving that moon from contamination by microbes that might have survived aboard the spacecraft. Jupiter research did not end with Galileo. Juno arrived in 2016 to study the planet's origin, interior, atmosphere, and magnetic field. Its first polar orbits also brought new observations of the Galilean moons. Other missions have used Jupiter for gravity assist while collecting additional measurements. Together, these encounters reveal a system rather than a solitary planet. Jupiter has faint rings made largely from dust released when small particles strike inner moons, and has irregular distant moons, many probably captured or produced by collisions. It has radiation belts, plasma currents, and auroral connections linking the giant planet with its satellites. Even the small bodies leave marks upon the atmosphere below. The system is active on every scale, from the deep flow of metallic hydrogen to volcanoes on Io and cracks in Europa's ice. As we move outward again, Jupiter slowly shrinks behind us. The sunlight continues to weaken, and the interval to the next planet spans hundreds of millions of kilometers. The next giant is less massive, less dense, and surrounded by the most extensive bright ring system visible from Earth. Saturn appears calm through a small telescope. Its globe is pale gold. The rings seem solid and perfectly arranged, tilted into a graceful ellipse. The view can look almost artificial, as if the planet had been designed to represent astronomy itself. Nothing about the ring system is solid or still. Saturn is the sixth planet from the Sun and the second largest. Its average distance from the Sun is about 9.5 astronomical units. Sunlight takes roughly 80 minutes to reach it, with the exact time changing as the planets move. Like Jupiter, Saturn consists mainly of hydrogen and helium, and has no solid surface on which a spacecraft would land. Gas becomes progressively denser with depth, passing into fluid states under immense pressure. Saturn is much less dense than Jupiter. Its average density is lower than that of liquid water. The familiar statement that Saturn would float in an ocean is mathematically playful but physically impossible. No container or body of water could hold the planet, and Saturn's outer material would not remain an intact ball under such conditions. The comparison nevertheless communicates how much of the planet is made from light elements. Saturn's interior is thought to contain a central region rich in rock, ice, and heavy elements, surrounded by metallic and molecular hydrogen. Data from Cassini suggests that the transition between core and envelope may be diffuse rather than a sharp boundary. The planet emits more energy than it receives from the Sun. Slow contraction contributes, and helium is thought to separate from hydrogen in parts of the interior, falling deeper and releasing gravitational energy. This process is sometimes described as helium wave. Above, the visible atmosphere is arranged into bands and jet streams. Saturn's colors are softer than Jupiter's because haze in the upper atmosphere obscures some deeper contrast. Winds near the equator can reach hundreds of meters per second. Rotation is rapid with a day of roughly 10.5 hours. Measuring it precisely is difficult because Saturn has no solid surface and its magnetic field is unusually aligned with its rotation axis. Different methods have therefore produced slightly different values. At the North Pole is a six-sided jet stream known as the hexagon. It surrounds a central polar cyclone and extends across tens of thousands of kilometers. Laboratory experiments and atmospheric models show that rotating fluids can support polygonal wave patterns. The hexagon is not a rigid geometric structure placed upon the planet. It is a persistent wave in a moving atmosphere. Its color changed as Saturn's seasons progressed during the Cassini mission, probably because sunlight altered the production of atmospheric haze. Saturn takes about 29.5 Earth years to orbit the Sun. Each season therefore lasts more than 7 years. The rings cast changing shadows across the planet, while the angle at which we view them from Earth slowly opens and closes. At ring plane crossing, the rings can nearly disappear through a telescope. This happens because their vertical thickness is extraordinarily small compared with their width. The main rings extend for tens of thousands of kilometers, yet many regions are only around 10 meters thick. They are not a flat, unbroken disk. They consist of countless separate particles, most composed predominantly of water ice. Sizes range from fine grains to boulders, with occasional much larger structures or embedded moonlets. Each particle revolves in Saturn according to the laws of orbital motion. The material closer to the planet moves faster than material farther away. The wings are therefore a vast collection of individual orbits rather than a wheel rotating as one object. From a distance, the countless particles merge into broad named bands. The right main rings are called A, B, and C. Fainter rings lie inside and outside them. The Cassini division appears as a dark gap between the A and B rings, but it is not completely empty. It contains thinner inlets and particles whose distribution has been shaped by orbital resonance, particularly with the Moon and Mammoth Straw. Across the rings, gravity creates structure. Moons open gaps, confine narrow rings, and launch spiral waves. A tiny dashness travels within the Keeler gap, raising ripples along its edges. During Saturn's equinox, Cassini photographed the long shadows of these waves, turning small vertical features into visible dark lines. Other patterns arise where particles share orbital relationships with moons farther away. A small repeated tug can create a wave extending through thousands of kilometers of ring material. Collisions also matter. When particles strike one another, exchange energy, clump temporarily, and separate. Their combined gravity can form fleeting structures. Electrostatic effects may lift fine icy dust above the main plane, producing radial markings known as spokes. The rings are therefore active and evolving. The padeful from them enters Saturn's atmosphere in a process called ring rain. Micrometeoroids add darker contaminants. Moons can both remove and supply particles. Enceladus feeds the broad, faint E-ring with ice released from its plumes. This movement makes the origin and age of the main rings difficult to determine. One influential interpretation of Cassini measurements argues that the bright ring is comparatively young, perhaps between tens and hundreds of millions of years old. Their relatively low mass and limited contamination support this conclusion under certain assumptions. Other studies allow older rings that have been renewed, cleaned, or evolved in ways not fully represented by those models. The age remains debated because scientists must infer history from the ring's present mass, composition, pollution, and rate of material loss. They may have formed when a moon or icy body was disrupted inside the distance where Saturn's tides prevented the fragments from gathering into one world again. More than one formation path remains possible. Whatever their precise age, the rings are temporary on astronomical timescales. They lose material, spread, and interact with the atmosphere and moons. Saturn did not necessarily always look as it does now, and it will not retain the same rings forever. For 13 years, the Cassini spacecraft watched this changing system from orbit. It measured the planet, passed close to the rings, observed seasons, and repeatedly visited the moons. During its final 22 orbits, Cassini crossed the unexplored gap between Saturn and the innermost ring, using the planet's gravity to help estimate the mass of the rings. The mission ended in 2017 with a deliberate descent into Saturn's atmosphere. Like Galileo Jupiter, Cassini was destroyed in part to avoid an uncontrolled future collision with a potentially habitable moon. Its most consequential discoveries lay beyond the rings. One moon carries a thick nitrogen atmosphere, rivers and seas made from hydrocarbons. Another is small and icy, yet sends water-rich plumes into space from an ocean hidden below its south pole. The next part of Saturn's story belongs to Titan and Enceladus. Titan is larger than the planet Mercury, yet from outside, its surface is hidden behind a dense orange haze. The atmosphere is so substantial that Titan appears less like an airless moon and more like a small world wrapped in weather. It is the only moon known to possess a thick atmosphere, and the only place beyond Earth known to maintain stable bodies of liquid on its surface. Those liquids are not water. At Titan's average surface temperature, around minus 179 degrees Celsius, water ice behaves much like rock. Methane and ethane can exist as gases, liquids, or frozen material, allowing them to circulate through a weather cycle. Methane evaporates, forms clouds, and falls as rain. It gathers in channels, lakes, and seas before returning to the atmosphere. The details differ greatly from Earth's water cycle, but the underlying pattern is recognizable: evaporation, clouds, precipitation, runoff, and surface storage. Most of the large lakes and seas lie near Titan's north pole. Radar observations from Cassini mapped shorelines, channels, and dark smooth surfaces interpreted as liquid hydrocarbons. Some lakes are surrounded by steep-sided depressions. Sea levels and coastlines can change with seasons, though the slow pace of Saturn's orbit makes those changes difficult to observe across a short mission. Near the equator, enormous dune fields stretch for long distances. Their grains are not ordinary silicate sand. They are thought to be made from organic rich material created in the atmosphere, processed at the surface, and gathered by winds into long parallel ridges. In planetary science, organic means that a compound contains carbon in particular chemical arrangements. It does not automatically mean that the material came from an organism. Titan's organic chemistry begins high above the ground. Ultraviolet sunlight and energetic particles break apart nitrogen and methane molecules. Their fragments recombine into increasingly complex compounds. Some form aerosols, tiny solid or liquid particles that create the orange haze. These particles drift downward and coat the landscape. Sunlight continually destroys atmospheric methane, so some process must replenish it over geological time. Methane may be stored inside Titan and released through geological activity, but the rate, pathway, and history remain uncertain. For Cassini, scientists could not see the surface clearly at visible wavelengths. Radar and infrared instruments gradually assembled the global picture. One part of the Cassini spacecraft traveled farther. The Huygens probe, built by the European Space Agency, separated from Cassini and entered Titan's atmosphere in January 2005. A heat shield protected it during entry. Parachutes then slowed the descent while instruments measured winds, pressure, temperature, and atmospheric composition. Huygens emerged beneath the haze and photographed branching channels leading across brighter high ground toward darker plains. It landed on a surface scattered with rounded pieces of water ice, shaped in a way consistent with past transport by flow and liquid. The probe survived for a little over an hour after landing. Its images remain the only photographs taken directly from the surface of a world in the outer solar system. At ground level, Titan's pressure is about 1.5 times Earth's sea level pressure. The atmosphere is dominated by nitrogen, with methane and smaller amounts of other gases. A person could not breathe it, and the cold would be rapidly fatal without protection, because the air is dense and gravity is low. Flight is comparatively easy. Titan is an unusual place where a properly designed aircraft can travel through the atmosphere more readily than it could on many other worlds. The surface may not be Titan's only liquid environment. Gravity and rotation measurements support the presence of a global subsurface ocean, probably containing salty water mixed with ammonia beneath a thick shell of water ice. This creates two very different chemical settings. On the surface, liquid methane and ethane interact with complex carbon compound at extremely low temperatures. below, liquid water may exist in contact with layers of ice and perhaps, depending on the interior structure, rocky material. Scientists sometimes discuss the possibility of unfamiliar life using liquid hydrocarbons rather than water. This is a serious theoretical question, but there is no evidence that such life exists. Chemistry proceeds slowly in Titan's cold environment, and it is not known whether hydrocarbon liquids can support the organization and energy flows required for biology. The subsurface ocean is a more familiar candidate for habitability, but it too remains poorly understood. A body of liquid water is not enough. Its chemistry, energy sources, duration, and exchange with other layers all matter. Titan's importance does not depend on finding life. It is a natural laboratory for atmospheric chemistry, weather, and the baby of organic material. It shows that landscapes resembling rivers, dunes, and seas can arise from substances very different from those shaping Earth. If Titan is large, hazy, and complex, and Cellulus first appeared almost ordinary, it is a small moon only about 500 kilometers wide. Its surface is bright because freshwater ice reflects much of the sunlight falling upon it. Some regions are heavily cratered, while others are smoother and younger. Near the South Pole, long fractures cross the surface. They are informally called tidal stripes. These parallel fissures are warmer than the terrain around them and open into an active interior. Cassini discovered jets of water vapor and icy particles erupting from the fractures into space. The particles spread into a plume above the South Pole, and much of the escaping ice supplies Saturn's broader E-ring. The spacecraft repeatedly flew through this material. Instead of drilling through kilometers of ice, Cassini sampled particles delivered naturally from below. Its instruments detected salts, silica grains, organic compounds, methane, carbon dioxide, hydrogen, and other materials. The combination provides evidence for a global ocean beneath the icy crust and for chemical reactions between water and warm rock at the seafloor. Tiny silica particles are especially informative. Their size and composition are consistent with formation where hot water interacts with silicate rock, followed by transport output to the ocean. Molecular hydrogen in the plume can be produced through water-rock reactions, such as actinization. On Earth, hydrogen released to hydrothermal systems can provide chemical energy for microorganisms. Its presence at Enceladus therefore strengthens the case that the ocean contains an energy source potentially useful to life. Phosphorus has also been identified in ice grains originating from the ocean. Along with carbon, hydrogen, oxygen, and sulfur, it belongs to the set of elements important to life on Earth. These findings do not amount to a detection of life. Water, organic molecules, useful elements, and chemical energy establish a potentially habitable environment. They do not show that biology ever began there. The same ingredients can exist in non-living systems. Enceladus remains active because of tidal heating. Its slightly changing orbit causes Saturn's gravity to flex the Moon. The resulting heat helps maintain liquid water. Interaction with neighboring moons contributes to the orbital arrangement that keeps this heating alive. The ice shell is not equally thick everywhere. It is thinner near the South Pole, where the fractures release heat to material. The jets become stronger and weaker as Enceladus travels around Saturn, responding to changes in tidal stress. Titan and Enceladus overturn a simple idea about the habitable zone. At the distance of Saturn, sunlight is far too weak to maintain liquid water on the exposed surface. Yet gravity can supply heat inside a moon. An ocean can remain hidden under ice, and chemistry can proceed without daylight. The traditional habitable zone around a star remains useful when discussing liquid water on the surface of the planet. It is not the only place where liquid water can exist. Several other Saturnian moons contribute to the system without requiring a complete catalogue. Mimas carries an impact crater so large relative to the Moon that the collision came close to disrupting it. Iapetus has one hemisphere much darker than the other, partly because just one distant 3B coats its leading side and triggers differences in ice migration. Small moons exchange material with the rings, open gaps, and maintain narrow edges. Saturn is therefore connected from its deep interior to the outermost dust. The planet shapes the rings. The rings exchange material with moons, and Saturn feeds wandering from an ocean. Titan's gravity guided Cassini through much of its long orbital tour. Beyond Saturn, direct exploration becomes sparse. Only one spacecraft has visited either Uranus or Neptune at close range. Voyager 2 passed Uranus in 1986 and Neptune in 1989. Most detailed knowledge of both planetary systems still rests on brief flybys, supported by decades of observations from Earth and space telescopes. The limits of the evidence become part of the story. Uranus is the seventh planet from the Sun and the first planet discovered with the aid of a telescope. William Herschel observed it in 1781. At first he thought it might be a comet. Careful measurements showed that it followed a nearly circular orbit far beyond Saturn, expanding the known scale of the planetary system. Uranus takes about 84 Earth years to orbit the Sun. Its most famous feature is not its color or size, but its orientation. The rotational axis is tilted by nearly 98 degrees relative to its orbital plane. The planet appears to turn on its side. This creates extreme seasons. Around the solstice, one pole points broadly toward the Sun, while the other faces a long darkness. A quarter of a Uranian year lasts about 21 Earth years. Over the orbit, sunlight gradually shifts from one pole to the other, and immense collision early in the planet's history may have produced the tilt. Models involving several smaller impacts or gravitational interactions have also been explored. Any explanation must account not only for Uranus, but for the orbits and orientations of its moons and rings. The entire inner satellite system broadly follows the tilted equatorial plane. This suggests that the eventual process occurred early enough for disk and material around Uranus to settle or reform afterward. Uranus is called an ice giant. The name does not mean that it is a solid frozen ball. Its outer atmosphere contains hydrogen and helium with methane that absorbs red light and contributes to the blue-green appearance. Deeper inside, models include a hot, dense fluid rich in water, ammonia, and methane components above a rocky core. Planetary scientists call these materials ices because of the compounds involved and the conditions under which they condensed in the early solar system. Under the pressure and temperature inside Uranus, they need not exist as ordinary household ice. The planet has no solid surface. The descending spacecraft would encounter increasing pressure and temperature until dust and fluid became part of a continuous deep envelope. Uranus radiates remarkably little internal heat compared with the other giant planets. Neptune, which is similar in size and composition, releases much more. The reason for this contrast is not known. Perhaps a past impact altered Uranus's interior and trapped heat beneath stable layers. Perhaps the distribution of material suppresses convection. With only one close flyby, models remain weakly constrained. Voyager 2 saw a comparatively bland atmosphere during its encounter, but Uranus was then near the southern summer solstice. Modern telescopes have observed bright clouds, storms, and seasonal changes as sunlight moves toward the equator north. The atmosphere can be extremely cold, reaching lower measured temperatures than Neptune despite Uranus being closer to the Sun. Its magnetic field is unusual. The magnetic axis is tilted almost 60 degrees from the rotation axis and is strongly offset from the center of the planet. As Uranus rotates sideways, the magnetosphere is swept into a changing, twisted configuration. This off-centered field may arise because the dynamo operates in a relatively shallow shell of conducting fluid rather than throughout a large metallic hydrogen region like Jupiter's. Uranus also has narrow dark rings. They were discovered in 1977 when the planet passed in front of a star and the starlight repeatedly dimmed before and after the main occultation. Voyager 2 later imaged them and discovered additional structures and small moons. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Their surfaces combine craters, faults, valleys, and evidence of geological renewal. Miranda is especially striking, with enormous cliffs and patchwork regions that appear to have been assembled from different episodes of deformation. Some Uranian moons may contain internal oceans, but present evidence is indirect and incomplete. The system has never received a sustained magnetic and gravity measurements that transformed understanding of Europa, Ganymede, and Enceladus. From Uranus, the journey to Neptune crosses another vast interval. Neptune orbits at an average distance of about 30 astronomical units. 1 year lasts nearly 165 Earth years. Sunlight there is roughly 900 times weaker than at Earth. The planet could not be discovered easily by unaided observation. Its position was predicted through mathematics. Astronomers noticed that Uranus did not move exactly as expected. Urbain Le Verrier in France and John Colch Adams in Britain independently calculated that the gravity of an unknown outer planet might explain the discrepancy. In 1846, Johann Galle and Heinrich der West searched near Le Verrier's predicted position and found Neptune. The episode is often celebrated as a triumph of Newtonian gravity, though the history also includes disputed credit, incomplete observations, and later revisions to the planetary masses used in the calculations. Neptune is the second ice giant. Its atmosphere contains hydrogen, helium, and methane. Familiar images often showed as a much deeper blue than Uranus, but some Voyager images were processed to enhance clouds in contrast. Reprocessed color comparisons indicate that the two planets are more similar in visible color than popular images imply. Neptune is not calm. It has the fastest measured planetary winds in the solar system, reaching more than 2,000 kilometers per hour in some regions. Bright methane ice clouds race through the atmosphere. Large dark storms appear and disappear. Voyager 2 photographed a great dark spot in 1989. A few years later, the Hubble Space Telescope could no longer find it, but other dark vortices have formed at different latitudes. These storms are not marks on a permanent surface. They are structures within a moving atmosphere. The energy driving such activity is surprising, because Neptune receives so little sunlight. The planet emits considerably more energy than it absorbs from the sun. Heat escaping from the interior helps power convection and weather. Why Neptune releases much more internal heat than Uranus remains one of the central puzzles of the ice giants. Neptune also has an unusually tilted and offset magnetic field, suggesting a dynamo operating in a shell of conducting material. It has faint rings, including regions where particles gather into brighter arcs, rather than spreading evenly around the orbit. Its largest moon, Triton, is unlike the regular moons that formed in orderly disks around their planets. Triton travels in a retrograde orbit, moving around Neptune in the opposite direction from the planet's rotation. This strongly suggests that it formed elsewhere and was captured. It may once have been an object of the Kuiper Belt. Capturing a large moon requires energy to be removed from its original motion. One leading model proposes that Triton once belonged to a binary pair. During a close encounter with Neptune, one member was ejected while Triton remained bound. Other interactions may also have contributed. The newly captured orbit would have been elongated and disruptive. As tides gradually made it more circular, energy was released as heat. Existing moons may have collided or been scattered, leaving the present Neptunian system reorganized around the newcomer. Triton's surface is extremely cold, dominated by frozen nitrogen, water, and other volatile compounds. Voyager 2 found few impact craters, suggesting substantial resurfacing. It also observed dark plumes rising several kilometers above the ground and drifting downwind. These were purportedly powered when weak sunlight penetrated translucent nitrogen ice. Warmed dark material below and caused nitrogen gas to build pressure before escaping. Other internal processes may contribute to Triton's geology. Triton may contain a subsurface ocean sustained by radioactive and tidal heating, but the evidence is less direct than for Europa or Enceladus. Its orbit is still evolving. Tidal interaction draws Triton slowly inward. Far in the future, it may pass within Neptune's Roche limits and be torn apart, perhaps creating a ring system more substantial than the one Neptune has today. Voyager series flyby of Triton ended the spacecraft's tour of the planets. It had traveled past Jupiter, Saturn, Uranus, and Neptune, using gravity at each encounter to reach the next. After Neptune, its path bent away from the planetary plane and continued toward interstellar space. The planets were behind it, but the solar system was not over. Beyond Neptune lies a broad population of icy worlds. Some occupy stable residences, others follow tilted or stretched paths. Among them is Pluto, once seen as a lonely final planet, now understood as a member of a much larger frontier. The final stage of our journey begins there. Pluto was discovered in 1930 as a moving point of light. The astronomer Clyde Tombaugh found it while working at Lowell Observatory in Arizona. He compared for his rapid plates of the same region of sky, searching for an object that shifted against the background stars. The discovery completed the search inspired by small apparent irregularities in the orbits of Uranus and Neptune. Those irregularities did not in the end require Pluto. Improved measurements show that a predicted disturbance had largely resulted from an inaccurate estimate of Neptune's mass. Pluto was also far too small to produce the expected effect. For much of the 20th century, its size remained uncertain. It appeared only as a distant point, and estimates depended partly on how reflective scientists assumed its surface to be. The discovery of its largest moon, Saturn, in 1978 allowed the mass of the system to be measured far more accurately. Pluto gradually became smaller in the scientific imagination, but more interesting. It follows an elliptical, tilted orbit that takes about 248 Earth years to complete. At some points, it travels closer to the Sun than Neptune does. Two worlds cannot collide because their orbits are protected by unstable resonance. Pluto completes 2 journeys around the Sun for every 3 completed by Neptune. Their timing and orbital geometry keep them safely separated. This 3-to-2 resonance also connects Pluto to a wider population of trans-Neptunian objects known as Plutinos. Pluto is therefore not an isolated exception, wandering beyond the planets. It is part of a structured region shaped by Neptune's gravity. The distance made close exploration difficult. NASA's New Horizons spacecraft launched in 2006. It traveled past Jupiter for a gravity assist and continued through the outer solar system for more than 9 years. Because it was moving too quickly and carried too little fuel to enter orbit, the encounter with Pluto would be a flyby lasting only hours at its closest point. Years of preparation depended on a narrow window. The spacecraft had to aim its instruments, collect observations, and store them without waiting for instruction from Earth. A radio signal took several hours to cross the distance in one direction. The full collection of data required more than a year to transmit home through the spacecraft's limited connection. Before the encounter, even the best images showed a blurred pattern of light and dark. New Horizons revealed mountains, glaciers, plains, haze, and evidence of active geology. The most recognizable feature is a bright heart-shaped region called Tombaugh Regio. Its western lobe contains Sputnik Planitia, a vast basin filled mainly with nitrogen ice. Unlike water ice at Pluto's temperature, nitrogen ice is soft enough to flow over geological time. The surface of Sputnik Planitia is divided into large, polygonal cells. These are interpreted as evidence of convection, with warmer nitrogen ice rising slowly, cooling and sinking again. The planet has very few visible impact craters, indicating that its surface has been renewed comparatively recently. Along its edges rise mountains several kilometers high. They are made primarily from water ice, which at these temperatures behaves as strong bedrock. Glaciers of nitrogen ice appear to flow around and between them. Other regions are older and densely cratered. Long faults suggest that Pluto's interior expanded as it evolved, perhaps as an internal ocean gradually froze. Models allow liquid water to remain deep beneath the surface, but its present extent is not known. Pluto also possesses a thin atmosphere dominated by nitrogen, with methane and carbon monoxide. When the dwarf planet moved closer to the Sun, surface ices warm and sublimate into gas. As Pluto moves farther away, some atmospheric material can freeze back onto the ground. The atmosphere is therefore connected directly to seasonal transport across the surface. New Horizons photographed many delicate haze layers extending high above Pluto. Sunlight drives chemistry in the atmosphere, forming particles that settle and contribute to the reddish-brown colors of the landscape. Pluto is cold, but not simple or dead. Its surface is renewed by volatile ice. Its atmosphere changes. Its interior may retain heat. The flyby replaced an indistinct point with a world whose geology remains only partly explained. But Charon is central to that world. It's about half Pluto's diameter, unusually large compared with the body it accompanies. Both Pluto and Charon orbit a common center of mass located outside Pluto itself. This is why they are sometimes informally described as a double dwarf planet system. The label is not an official separate classification, but it captures the balance of their motion. They are mutually tidally locked. Charon always shows the same face to Pluto, and Pluto always shows the same face to Charon. From the Pluto-facing hemisphere, Charon would remain fixed in the sky, rather than rising and setting. Charon's surface is dominated by water ice and cut by enormous canyons. The contrast between its northern reddish region and more neutral terrain may result partly from material escaping Pluto, reaching Charon and being chemically altered by radiation. 4 much smaller moons travel around the pair. Their irregular shapes and rapid, complicated rotations may preserve the aftermath of the event that formed Charon, probably a major collision early in the system's history. Pluto's classification changed before New Horizons arrived. The change followed a wider discovery. Beginning in the 1990s, astronomers found increasing numbers of objects beyond Neptune. Some occupied orbits resembling Pluto's. Then Eris was discovered, a distant body comparable to Pluto in mass. The solar system now appeared to acquire either a broader definition that might admit many planets, or a new boundary between planets and the growing trans-Neptunian population. In 2006, the International Astronomical Union adopted a formal definition for planets in the solar system. Under that definition, a planet orbits the Sun, has enough mass for gravity to pull it into a nearly round shape, and has cleared the neighborhood around its orbit. Clearing does not mean removing every pebble or moon. First, it shares its broad orbital region with near-Earth asteroids, and Jupiter travels with Trojan asteroids. The criterion concerns gravitational dominance. A planet contains overwhelmingly more mass than other bodies occupying comparable orbital territory and is strongly organized or removed much of the surrounding population. Pluto is round and orbits the Sun, but it travels within the Kuiper Belt among many related bodies. It does not meet the adopted clearing criterion. The IAU classified it as a dwarf planet. A dwarf planet, in this definition, orbits the Sun, is approximately round, is not a moon, and has not cleared its orbital neighborhood. Despite the name, the IAU treats planet and dwarf planet as distinct categories rather than making one a subtype of the other. The decision remains debated. Some planetary scientists prefer geophysical definitions based on the nature of a body rather than its orbital surroundings. Under such approaches, Pluto and many large moons can be discussed as planets because they are complex, differentiated worlds. The disagreement is about how a scientific word should organize nature. It is not a disagreement over whether Pluto has mountains, weather, or geological importance. Classification did not demote the physical world. It placed Pluto within a newly recognized family. Other officially recognized dwarf planets include Ceres in the asteroid belt and several bodies beyond Neptune, including Eris, Haumea, and Mycmaec. More distant objects may eventually join the category as their sizes and shapes become better established. The Kuiper Belt begins beyond Neptune and extends through a broad, thick disk of icy objects. It is sometimes called the third zone of the solar system, after the rocky inner region and the realm of the giant planets. Its objects contain mixtures of rock and frozen water, methane, ammonia, and other volatile compounds. They vary in color, size, and orbital history. Many have moons, and binary systems are common enough to provide important clues about how the population formed. But the belt is not distributed evenly. Some objects occupy a relatively stable classical orbit, Astronomers use the terms called in hot classical populations, but these names describe orbital behavior rather than temperature. Cold classical objects have less tilted, less disturbed orbits. Hot classical objects travel on more inclined and dynamically excited paths. Other bodies are held in resonances with Neptune. Pluto belongs to the 3-2 group. Different resonances create additional families at particular orbital distances. Beyond and overlapping the main belt lies the scattered disk. Its bodies follow more elongated and inclined orbits, often as a result of past encounters with Neptune. Some travel hundreds of astronomical units from the Sun before returning to the region of the outer planets. Still more detached objects circle distant orbits that Neptune does not strongly control today. Their paths may preserve the effects of early planetary migration, passing stars or undiscovered populations. Speculation about distant planets arises partly from attempts to explain usual orbital patterns, but no proposed additional large planet should be treated as discovered without direct supporting evidence. The Kuiper Belt once contained much more material than it does now. Models of giant planet migration suggest that Neptune moved outward through an early disk of icy planetesimals. Gravitational encounters scattered much of that material. Some objects were ejected completely, some were sent to distant reservoirs, others became trapped in resonances or left on the orbits observed today. The belt is therefore a record of planetary movement. New horizons continue through it after Pluto. In 2019, the spacecraft flew past a small object now named Arrokoth. Arrokoth consists of two flattened lobes gently joined together. Its shape supports models in which small bodies can form through the slow gathering and collapse of local clouds of particles rather than through a sequence of violent high-speed collisions. It is one example from an enormous population. Most Kuiper Belt objects will remain points of light for the foreseeable future. Beyond the belt, the distances expand again. The scattered disk can reach hundreds of astronomical units, but the Oort Cloud is thought to begin thousands of astronomical units from the Sun. No spacecraft has entered it, no telescope has photographed the cloud as a structure. Its existence is inferred mainly from long-period comets. These comets approach the inner solar system from many directions rather than remaining close to the shared plane of the planets. In 1950, the Dutch astronomer Jan Oort proposed that they come from a vast, roughly spherical reservoir surrounding the planetary system. Current estimates place the inner region somewhere around 2,000 to 5,000 astronomical units from the Sun. The outer extent may reach tens of thousands of astronomical units, possibly as far as 100,000. The uncertainty is enormous because the cloud has not been directly observed. Its objects probably form much closer to the Sun. Encounters with the growing giant planets scattered them outward. Some escaped the solar system, while others remained weakly bound. The gravitational influence of the Milky Way and passing stars then helped reshape their orbits into a broad shell. At those distances, the Sun is no longer the only important gravitational influence. A small disturbance can send an icy body on a journey lasting millions of years toward the inner planets. Voyager 1, despite being the most distant human-made object, will not begin crossing the Oort Cloud for centuries. Passing through the full region could require tens of thousands of years. This fact introduces the final question. Where does the solar system end? One answer uses planets. Neptune is the outermost recognized planet at about 30 astronomical units, but the Kuiper Belt lies beyond it, so the planetary boundary cannot be the boundary of everything orbiting the Sun. The second answer uses a woolly wind. Particles continually flow outward from the Sun, carrying magnetic fields and inflating the heliosphere. Far beyond the planets, this wind encounters the local interstellar medium. The first major transition is the termination shock. Here, the supersonic solar wind slows abruptly as it begins to respond strongly to the pressure beyond. Past this boundary lies the heliosphere, where the solar wind is compressed, heated, and redirected. Farther outward is the heliopause. At the heliopause, the outward pressure of the solar wind balances the surrounding interstellar environment. Beyond it, particles and magnetic conditions are dominated by interstellar space rather than the solar wind. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed in 2018. Both therefore entered interstellar space in the heliophysical sense. They did not leave every part of the solar system. The sun's gravity still governs their long trajectories, and the Oort Cloud lies vastly farther away. Leaving the heliosphere is not the same event as traveling beyond the sun's gravitational family. The position of the heliopause is not fixed. It changes with solar activity and with conditions in the interstellar medium. The shape of the heliosphere is more complicated than a simple teardrop diagram, and measurements continue to revise models of its boundary and tail. A third answer therefore uses gravity. The solar system might be said to end where objects are no longer bound primarily to the sun, beyond the outer Oort Cloud and in a region where the gravity of neighboring stars in the galaxy becomes more important. There is no sharp wall there either. Gravitational influence fades with distance and overlaps with other influences. The Oort Cloud itself may be disturbed, replenished, or stripped during encounters over the sun's journey through the galaxy. The edges do not agree because they answer different questions. Neptune marks the end of the planets. The outer Kuiper region marks the end of the main disk of small icy worlds. The heliopause marks the end of the solar wind's dominance. The Oort Cloud approaches the outer reach of objects still loosely held by the sun. Each is a useful boundary. None is the single line shown around a single diagram. The Voyager spacecraft continue beyond the heliopause, carrying instruments, records, and the golden records attached to their sides. Their electrical power gradually declines, and individual systems cannot operate forever. Even when communication ends, the spacecraft will continue moving through the galaxy. They will not arrive at another planetary system on any human timescale. Their journeys are better understood as long drifts through interstellar space, passing stars at great distances as both the spacecraft and the stars follow their own paths around the Milky Way. From Voyager, the sun is still the brightest star in one direction, but it is only a point. The planets can't be resolved with unaided instruments. The architecture that fueled our journey collapses into darkness and geometry. Looking back, the solar system is not a rarefied world. It is a star holding almost all the mass. It is an inner region of rock and metal, followed by fragments, dwarf planets, and comets. It is a realm of giant planets surrounded by systems of rings and moons. It is a distant disk, reshaped by migration, a magnetic bubble pressed against interstellar space, and perhaps a spherical cloud reaching a significant fraction of the distance to the next star. It is also history. The craters of Mercury preserve early impacts. Venus records the power of an atmosphere. Earth and the Moon revealed a shared beginning, followed by different paths. Mars holds the remains of rivers and lakes. Asteroids and meteorites preserve planetary building materials. Jupiter's gravity heats moons and redirects small bodies. Saturn's rings change while hidden oceans endure beneath ice. Uranus and Neptune remind us how much remains unknown after a single brief encounter. Pluto demonstrates that a small world can sustain glaciers, weather, and active geology far from the sun. No region exists entirely alone. Gravity establishes resonances across immense distances until it moves between surfaces and atmospheres. Moons supply rings. Impacts exchange rock between planets. The solar wind raises every planetary orbit, then finally weakens against the material between the stars. Our journey began beneath an ordinary night sky. The points of light looked close enough to share one dark ceiling. The true distances were hidden, and the spaces between them seemed empty. We can now replace that simple ceiling with a moving structure. Earth travels around an active star. The star moves around a galaxy. Every planet follows its own path, accompanied by moons, dust, and fragments. Far beyond the last planet, unseen objects continue their slow orbits through a darkness in which sunlight may take months to arrive. There is no need for the journey to end at a wall. The solar system, fades outward through overlapping forms of influence, light grown weaker, solar particles giving way to interstellar space, and gravity loosening its hold across distances almost too large to imagine. Somewhere in that widening dark, the sun becomes one star among many, and around it still, traveling together, all the worlds we have passed,